My name is Gabrielle Vukasin. I'm a fifth-year PhD. My name is Gabrielle Vukasin. I'm a fifth-year PhD student at Stanford University in the Mechanical Engineering Department. And I'll be describing my work in minimizing energy loss in MEM resonators. So MEM resonators, or microelectromechanical resonators, are micro-sized transducers which operate at their resonant frequencies. They can be used as accelerometers, gyroscopes, or timing references. They're used in our everyday lives for things from crash detection for airbag deployment to sensors and timing references in the iPhone 10. It's important to understand how they work in order to optimize them for each of these applications. The motion of each resonator can be described by a 1D lumped parameter model. This is called the mass spring damper model, where an effective mass, spring constant, and damping constant describe their motion. The ratio of the energy stored in the resonator to the energy dissipated per cycle of the resonator is called the quality factor, or Q. Q is related to the mass, resonant frequency, and the damping of the resonator. So in most applications, we want to maximize Q in order to minimize the damping. This decreases power consumption and also creates resonators with higher spectral purity oscillations, which is important for timing references. Q is a reciprocal sum of the damping due to each of the damping mechanisms. There's gas damping, thermoelastic dissipation, the Akhiezer-limit, and anchor damping. Each of the damping mechanisms have a different temperature dependence, which allows us to quantify each mechanism and determine the limiting or largest damping mechanism. So the goal is to create a resonator with the highest Q possible. And so I did this by minimizing the damping mechanisms individually. So I minimize gas damping by encapsulating the resonator at a low pressure, thereby minimizing the interactions of the resonator with air molecules. I minimize thermoelastic dissipation by choosing a bulk mode resonator over a flexural mode resonator in order to decrease the heat loss due to the temperature gradient, which is induced by the resonator motion. This is much more prevalent in flexural mode resonators than bulk mode resonators. Lastly, I made the anchor more compliant in order to reduce anchor damping, which you can see here, the springy anchor. This leaves us with the limiting mechanism, or the largest damping mechanism, of QAKE, which is the Akhiezer-limit. This is the material loss limit, and which in our case is silicon. This is the best Q that we can possibly achieve. And so I published these results in the Journal of Microelectromechanical Systems.